So here we are all super space theme place. And Camila, if you can help me install a screen here.
Yeah, I will put the screen. You can start sharing, and then I will
yeah,
just...
Indeed, I'm gonna start sharing already.
Can you share?
Oh, yes, right now. Oh, there you go. Okay, perfect. So I think everyone can see the screen already. Oh my God, this is amazing. Yeah. I'm really in love with this place because it's how you can see the sun there, just like in the earth. This place is amazing. Okay, guys. So welcome everyone. So as you know already, we will learn today about satellite engineering and applications. Okay. Sorry, no, someone's talking. Okay, so what's the idea of this class of today? The idea is that we will have 5 different classes. Okay, we will go through different topics, all regarding satellites. But we're going to start with spacecraft design. Why spacecraft design before talking about actual satellites? Because we need to understand why we are, what we want to make satellites, which application, which reason we have to actually make this spacecraft. In the second class, we're going to learn about orbital mechanics, because the way things move in space is really different on how things move here on the Earth, because here in the Earth we are bounded to the gravity of Earth, but in space we're bounded to also to the gravity of Earth, but in a very, very different way. We will be moving super fast around the planet, or around another asteroid, or around the moon, around another planet of the sun. Okay, so these 2 first parts is to learn about more theory about satellites, and then we will start learning in the 3 last classes about satellite applications, and the idea is to understand how we can use this spacecraft to improve life on Earth. And some examples of that can be, for example, GPS, or we want to take pictures of the Earth, etc. Okay, so I'm going to present myself. I'm Sebastian Ogalde. I'm the guy that you're seeing here. I'm an electronics engineer from Chile. I come from Chile. You may know this little long country in the end of the world. It's a beautiful place. I used to work as an integration and testing engineer for the Euclid satellite, which is actually a super big, amazing satellite from the European Space Agency. I'm going to show some pictures later on. I'm also an automotive engineer for General Motors, currently based in Turin. Okay, I work in Italy. And I'm also a space entrepreneur, since I'm a CEO and founder of Andes Aerospace, which is a Chilean satellite company based also in Chile. I'm also founder and director of Chilean Space Hub and Analog Astronauts. If you have any questions about all these other things, you feel free to ask me at any moment that you want. Okay, so just to give you some examples that cool things that you can make with satellites. This is more or less what I was doing a couple of years ago. I was working with this amazing satellite, which is a space telescope. This is more or less, this is like the competitor of a James Webb telescope. And I was working there, building this satellite and testing, making sure that everything works correctly. So with this, you can make yourself an idea that I know a little bit about satellites. So that would be really, really good for our lecture. So the first class, as I told you already, is going to be about spacecraft design. Thank you. So, okay, so since we already started with one model here, actually you can move freely. There's no problem. So this satellite is actually really similar to Euclid. It's not Euclid, but it's also a space telescope. Okay, so if you come here closer, you
This
can
is
see
Kepler. This is the Kepler Space Telescope.
amazing. Oh yes, I see the name now. So this is the Kepler Space Telescope. It's a space telescope. And for example, if you come here, if you see this part of the satellite, you will see that this actually looks like a propulsion, but actually it might be, I'm just checking here behind. This might be either propulsion or it can be a camera, okay? So why a camera if the telescope is over there? A camera here, you will need a camera here because you would like to know where the satellite is pointing to. So if you have, for example, a catalog of all the stars that are currently right now in the sky, with these cameras, you can actually understand where you're looking at because you know exactly how the sky looks like in a certain direction. So you can know where you're pointing. There are many subsystems in these satellites, and we are going to go through each of them, okay? So into the different categories in the presentation that you see behind me, okay? Okay, so in general, what you can do with satellites is you separate it in two different parts, okay? So I know we see a lot of text here. It's just for reference for you. But the idea is that we have two parts. You see a satellite, you talk with a space engineer, you talk with a satellite engineer, and you can always ask him or her, what's the payload and what's the bus or what's the service module, okay? So the first part is the bus or service module, or in this case, you can talk about supporting structure for the payload. So you have to think that satellites are made with a certain purpose, okay? So if a satellite is made with a purpose of observing the sky, for example, or taking pictures, you can think about it as a camera, okay? So you will have a camera and maybe a series of lenses, and that's going to be the payload. But you need to have some different systems around that camera that help the camera work correctly. So in this sense, if the camera, for example, needs power, you will need a power system. If you need to point the camera, maybe you will need a propulsion system. Okay, so if you need the camera to send the information back to Earth, you will need a telecommunication system. So all the systems that are not actually the purpose that you sent this satellite to space are the supporting system or the service module. Okay, so for example, if you see that in the presentation, you will see you can have power, you can have attitude control, command and data handling, telemetry, tracking and control, thermostructural, even the structure of the satellite is a support system for the payload. Okay, and then we talk about the second part, which is the payload itself. So we were talking about an example of a camera for a satellite. But there are other satellites that work as a GPS. So, for example, you will need special antennas for that. Or, for example, there are TV and streaming satellites. So you will need strong antennas also for that. You can have, for example, in general is that you can have antennas, you can have cameras, you can have telescopes, you can have whatever you want. That is actually the reason of this mission. Okay, so the idea, as I said in the beginning of this presentation, is that we have to understand what we want to accomplish with this spacecraft. You don't create a spacecraft just because for fun. Okay, we all want to do it because it's for fun. But we need a lot of money actually to create a satellite. So that's why we have to have in mind a purpose, an objective, a mission that we want to accomplish with this satellite. So in this sense, we try to answer this question by answering other questions that are more specific. Why are we doing this satellite? What's the mission objective? has this satellite been done before? Can I use already other satellites that are in space to accomplish the mission that I want to accomplish? And what are the level 1 requirements? What is the special mission that we want to accomplish with this satellite? Okay, so as you may have noticed, it's always about the mission. It's always about why we're doing this why we are sending this to space. So taking a more general approach, for example, and we stop talking about satellites and we talk more about the spacecraft, and we talk more about a general something that we want to take to space. We answer this question. We talk more about we have to the form will follow the function. Okay, so for example, if you need something that will be floating in space, you will need something more like this. But if you need something that will serve you to move here in the moon, you will need something more like the thing that I'm pointing to right now, which is the, oh my God, it disappeared. So this is the lunar rover that will have special characteristics that makes it suitable for the moon. And that's why it's so important to understand which are the characteristics of the moon if you're doing a moon vehicle, because you need to understand, for example, which is the pressure that you're going to put here in these wheels, which kind of payload that you're going to put here in the vehicle. For example, you have a camera here, you have a special antenna for communication. You can have a certain kind of propulsion. Maybe you don't want to have normal fuel because in less gravity you will have problems with this kind of fuel that will not have the same way of combustion, or it can be too dangerous for these conditions. So all these things, all these characteristics accompanied with the mission objective that you want to accomplish will determine how I'm going to create my spacecraft, or in this case, this is something more different kind of spacecraft that actually will move on the surface of the moon. Okay, so in that sense, form follows the function. Okay, so in the presentation you can see, for example, we have suborbital, we have orbiters, we have probes, we have landers, we have surface mobility, for example, as we are seeing now. So all these things are like spacecraft. These are space somethings that are designed in a very different way with very different objectives. Okay. So now we're going to talk more about, okay, we have the objective. We want to create a satellite that does something, and we know more or less how to create it. So you need a team for that. You need to understand how you're going to organize that in your in the time. For example, okay, I have 2 years to create this satellite. How I'm going to create the satellite? Which teams are going to work on what? So this is why it's important to define, to work on mission systems engineering. So, for example, if you want to do something with science, you have to have scientists in your team. If you want to send something close to the sun, you will have to have engineers that will work with sun simulations and thermal shields, for example, to protect your satellite from the sun, from the rays of the sun, because it's going to be super, super hard. You will have to have special electronics engineers that work with special coatings, maybe for the microchips that will be on the electronics that will be there in the satellite, that they will continue to work properly after they are exposed, I don't know, to 200, 500 degrees. Okay, so these people will give you a technical oversight of the mission. They will tell you that is possible, that is not possible. We want to do something that wants to go to the sun. Okay, you cannot do that because the sun is too hot. So we need to take into consideration other techniques. Maybe we need to have a minimum distance from the sun that will not damage the satellite. So all these people will have these functions that they are going to observe. Also, the design processes. Are the proposers of this satellite correct? Are they proper for the objective that we are following, etc. Okay. Okay, this is an amazing satellite. I love it actually. Okay, so as I was saying, the satellite is super complex. So you have to separate it into different systems. And actually, the story doesn't end if with the satellite. Okay, just imagine you finish your satellite, you build it, perfect. We launch it. Okay, we launch it. Amazing. Oh, everything is working. So what now? You have to use the satellite. So for that, you will have to have a space segment, which is the satellite itself, but also you will have a ground segment, which is going to be in charge of the launch, which is going to be in charge also of receiving the data, analyzing the data that is coming from the satellite, which is the mission objective, okay? And also you will have the user segment, which is people that are not related to the mission that want to use the satellite. For example, what happens with the satellites, the European satellites that take images from the Earth? All those images are available for you to download for free on internet. You can download all these images that are taken every day. So if you want to do science, for example, if Isha wants to do science now with those images, it's possible. You just need to go to the website and you download that information, and you can analyze that data for your application. And that happens a lot. That really happens a lot. Many scientists just go to this website and take this information for free, and they create new knowledge that helps humanity in different senses. Oh my God, this is amazing. They create this new knowledge that they then present in different, I don't know, conferences and presentations, or even, for example, in this kind of opportunities in which I can talk with people that are curious about space. Okay, so now we're going to talk about the first part, which is okay, I need to go back. Okay, so we were talking about these three different parts: space segment, ground segment, user segment. So we're going to go now to the space segment, which is the top one. Okay, so in this one, this is the actual satellite, and this actual satellite is super complex, and we need to divide it into different subsystems. Okay, so if you have this satellite, for example, I'm going to try to walk towards this satellite. So this satellite has to be resistant enough, mechanically speaking. Okay, I'm going to bring it closer to me. It has to withstand the pressure, for example, from the launch. So it has to be resistant enough to not to break into many parts while is it being launched. So that's why you need a good mechanical subsystem. You need also to have the possibility for this big thing to move. So you need for that propulsion. You need also for it to withstand the harsh conditions of space. So you need a good thermal subsystem. You need maybe these things to point into different directions. So you need an attitude control system. Okay, attitude, by the way, it means where you're pointing with the satellite. So for example, now my attitude is this one, okay? This is my pointing. What's the attitude of Sebastian now? It's not if he's angry or being, I don't know, but it's where I'm pointing to. Okay, so the attitude control of the satellite refers to that, refers to where we are pointing to. We need batteries also, so we need power conditioning and distribution subsystem. You need electromechanical, okay, maybe not always, but for example, in Euclid, in the satellite that I was working with, you needed some electromechanical parts because the antenna had to be deployed in space. because the antenna was too heavy and the motor was too tiny. So that had to be done in space. So for that, you needed a motor to be a tiny motor that needed to be mounted on the satellite. Then you have command and control electronics. So you need to send telecommands to this satellite. You need to control internally how it's working. And you need to download data, for example, or maybe change the orbit. So you can send commands from Earth to this satellite. You need communications, which is more or less what I was telling you before. And you also need flight software. So inside of this satellite, there are programs as the same kind of, well, not the same kind, but more or less the same thing that you're running on your computers right now, or the same thing that are running in our Meta Quest, for example. Okay, so these things have software. So the same thing happens with the satellite. You need to have software that will help the satellite accomplish its mission. And then you need to put the payload, which is the normally, not always, but it can be the science part of the satellite. It can be a camera, can be an antenna, special antenna, can be maybe some experiment that you're doing, etc. Okay, I went actually through all the subsystems, and the next slides are actually talking about this the subsystems. Okay, so designing a satellite is not hard because we don't have unlimited everything. Okay, so for example, you want to create the best satellite ever, but it's not possible because you have a limited budget. So if I don't know, Sammy wants to create a satellite that goes to the moon or orbits the moon, but you only have, I don't know, $250 million. So okay, that sounds like a lot of money, but then you know that the solar panels costs the solar panels that you want to put into that satellite cost the half. And then you tell me, no, I can't pay only for the solar panels the half of the money that I have. I have to pay for all the other things that I have to put in the satellite. So that's a constraint. That's a cost constraint that you need to decide which components, how much money you want to put for each component. And then you have to think about the physical constraints, because maybe you need a camera that has a certain price, but then you notice that this camera is not precise enough, doesn't have enough high resolution for the application, because you want to track, I don't know, you want to track ship movements in the sea, on the Earth, but the camera doesn't have enough resolution to actually see the ships on Earth. So that wouldn't make sense. So you have to change the payload and put better cameras on it. And by not forgetting also the money constraints, or not forgetting the physical constraints, because again, this process is iterative. You're going to have this process again and again and again, because maybe, okay, you found another camera that is better for ships tracking. Okay, perfect, but that camera is too big and my satellite doesn't have enough space for that camera. Okay, so maybe you have to think about having a bigger telescope or a bigger satellite. And that's why you have, when you are designing a satellite, you have a lot of different conversations to understand if this satellite can be built with the following indication, with the constraints that I have. Okay. So okay, so let's go to the next slide. Okay, let's go next slide. Oh, okay, for example, now we're going to go into different systems. Okay, so for example, if you have a mechanical system, the mechanical system talks about the structure of the satellite. So we were talking about the resistance of this satellite. So one thing is resistance, but also you need to think about if the material is lightweight enough. So maybe your satellite is going to be too heavy, and your propulsion system are not going to be good to move this satellite. or it's going to be too slow, and it's not compatible with the requirements of your mission. So for example, here, oh my God, this is amazing. You have here the nozzle of the the propulsion system of the satellite. So I don't know if we can actually make it visible for everyone. So maybe there you can see it better. So this, okay, I don't know this mission exactly, but most probably if you see that
This is a Venus mission. This is a
Venus
mission.
Okay, amazing, amazing. Actually, that's what I want to say, because if you have this kind of propulsion system, it's because you have to move into different orbits, like big orbits. So thanks, Camilo, because actually, wow, that was right. This satellite needs to go to Venus. So that's why you need a proper propulsion system. But coming back to the mechanical part, you need also resistance. You need weight to be good in the weight point of view. You need also to think about the grounding and electrostatics. So if your material gets charged so much so easily, that can be a problem for the electronics, right? Because if the structure is charged and then it's discharged into one of the microchips that control the satellite, well, the satellite can be then stop working, right? So we have to be really careful about all the decisions we take. And sometimes, sadly, this is what happens when you launch a satellite without knowing all the consequences of each of the decisions, of the design decisions that we're taking. Okay, so the common materials that you can find in mechanical systems for satellites are aluminum, titanium, beryllium, and carbon fiber. Okay, it depends on the satellite. Maybe some parts of the satellite will be done with carbon filter, and maybe some other parts of the satellite will be done with aluminum. Okay, so it's not necessarily you will be using only one material. It always depends on the mission, depends on the objective. Okay. So what kind of testing you have when you have this the mechanical part? You have, these actually are the most interesting tests, because they're like super super interesting in how they are done. So for example, one testing is the acoustic vibration. Okay, so what is the acoustic vibration? So you have to take into consideration that your super delicate satellite that you built with so much enthusiasm and like by taking care of each part of it, and maybe some sensitive camera, sensitive antennas. Okay, so I think we have a question over there, right? Or not? Yeah? You can go ahead if you have a question. No? Okay. So coming back to the topic, so for example, you have this satellite. So okay, so this amazing satellite that you're building will be put into a rocket, and rockets are not the most delicate thing. So you have seen the launches, and the launches are like crazy. They're like, they move a lot. They put your satellite into very, very harsh conditions that are not the same conditions in which the satellite is going to be in space. It's going to be something totally different. It's going to have a vibration like crazy. Okay, so this can be the vibration testing, but also you can have the acoustic testing. Okay, so in the acoustic testing, you will have this satellite being exposed to something like it's worse than the loudest concert that you might ever had in your life. Okay, so you put the satellite inside this anechoic chambers. Okay, you can find some on the European Space Agency and then in the Netherlands, for example, and there are some others across Europe, and obviously in the US there are going to be a lot of them as well. So they put this satellite inside this chamber, and then the chamber is going to have like a super big speakers, and then they're going to expose this poor satellite to super strong vibrations and sound. Okay, so this testing is super important, because if you designed your satellite in a way that is not resistant to that, you can say bye-bye to the satellite in the exact moment in which has been launched. Okay, so we don't want that. We want the satellite to survive and then go to Venus as we designed it, right? Okay, enough about mechanical. We can go to, okay, so the image that you're seeing right now are the simulations that you can do while you are working on this satellite. When you're designing it, there are specific software that can make simulations about how is the structure going to react under different loads. Okay, so that's the idea of doing this simulations on the computer. Okay, propulsion. Okay, so this is an amazing topic as well. So the idea about having propulsion is either to correct the attitude of the satellite. So if you recall, the attitude is where my satellite is pointing to. Okay, so maybe we need to change that. For example, if I have a little rocket in here and I'm in space, I can actually move like this, for example. Okay, or I can move to another side. So that's the idea. And that's super important if you have a camera, for example, a camera in your satellite, and you need to point to a certain place. So you need to have propulsion for attitude correction. There are other, okay, that's attitude control. That's the third point in the slides. So the first point of the slide is trajectory correction. So this is what happens when you launch your satellite. You will have the satellite moving in a certain orbit, and this is something that we're going to study later on in the in the orbital mechanics. So you will have your satellite move in a special way around the Earth, or around, I don't know, something else, the moon, for example, or Jupiter. And then you have to go, for example, from the Earth to the moon. So you have to insert your satellite into a different orbit than the one that it was having before. This is what trajectory. This is trajectory correction. So it's about the orbit itself. So if we want to change a little bit the orbit, but if we want to change planet, it's orbit insertion. Okay, and then we have RWA unloading, which is reaction wheels asynchrony unloading, and I'm going to explain that later because it can be more complicated. But basically, what you have is that sometimes in your satellites you can have like little wheels, like actual wheels. I don't know if Camilo, if we have reaction wheels. There are actual wheels that can be in space.
We don't have reaction wheels. Sorry.
Okay, but it's actually just a wheel that you put inside the satellite, and then if you start accelerating this wheel, the satellite itself is going to move the other way around. So you can use that for changing the attitude of the satellite.
Actually, when we look like a reaction wheel, we cannot see the wheel itself. Like in a satellite, it's just like in a cube. Because
exactly,
it's like encapsulated. So it's just like, it's closed. It's in a closed environment in order to avoid cross-contamination. But it's like the reaction will be like inside the cube. And it's actually located in one of like the corners of the satellite, depending on the attitude control we want to have on the spacecraft.
Exactly.
Sorry, Steph, go ahead.
No. I'm super happy that if someone else also has another comment to add, that would be also amazing. I really love to have this interaction. So also, if you have any questions, please just feel free to interrupt. It's not an interruption. It would be something actually super good to have this exchange. Okay. So there are the common types of propulsion. You have different materials, and it always depends on the objectives of your mission. But if one of them that I would like to talk about is the propulsion, which is a type of electrical propulsion that can be used, for example, to go to deep space. So it's super slow, super slow, but it's super efficient. So the thing is that you have the sun to charge the solar panels, and then you can use that to actually give propulsion to your spacecraft.
So this is a reaction. This is a ion engine.
Okay, perfect.
See, sorry, yeah.
This is amazing.
There you go.
Okay, so you can see it only if you come from this side. So yes, so it's super nice because you actually start applying some electrical energy to this thing. Okay, and then you can see it glowing, and it's actually particles that are going out from this. Well, it's not actual particles. It's like ions. Okay, that will be going out from. We'll start adding some momentum to your satellite, and that's how the propulsion works. So it's really amazing. It's really amazing. It looks super magical. Also, if you look it up on the internet, for example, it's like it looks like a light going out from the propulsion, and this light is actually giving momentum to the satellite. It starts to move. It's really crazy. It's really amazing. Okay. So, okay, we see some propulsion in the presentation. This is a propulsion system for maybe hydrogen. Okay, so this is pretty similar to what we saw in. Okay, now I'm getting inside a propulsion system. Okay, but this is this is a motor for a rocket. It's a propulsion system for a rocket, not for a satellite. But I don't know where's the other satellite, the Japanese one that was to Venus. But we had a system that was pretty similar to the one that we have here. Okay.
Here you go.
Amazing. Okay. Yes. So we had here in this one. Okay, yes, exactly. Okay, so we had a propulsion system pretty similar to the one that we're seeing in the presentation. Yes.
Would it be possible someday to get satellite fuel from space, from asteroids, for example, or?
Oh yeah, actually that is an idea sometimes about when people talk about astromining, is actually about getting materials, raw materials or processed materials, even in space itself, to help your if you want to stay in that place, for example, if you want to have propulsion for the satellite. I'm not quite sure about propulsion itself, but I have heard that, for example, people in the moon, if you find water in the moon, that's really nice because water has oxygen and has hydrogen. So you can use hydrogen for propulsion and you can use oxygen for breathing. So that's two good things. You have propulsion and you can breathe. So thanks for your question. Okay.
Thank you.
So, yes, okay, let's go back to the previous one.
We can even do mining in these asteroids here. We have a model of Tutatis here next to us, next to Europe. And then there's some asteroids around us. If we do mine on those, we can actually get some
Exactly.
materials for exploring the solar system.
Exactly. For example, I don't know, Camilo, if we can move this asteroid from the screen so the guys can see the image now. I cannot move it. I don't know why. But in any case, I will give you the introduction to what we're seeing now in the screen, which is the the thermal environment on space is super harsh. So you have to think that on Earth we are in a nice environment because we are protected from cosmic rays. We are protected more or less from UV radiation, and also the air provides us, the atmosphere itself provides us of some sort of compensation of temperature. So that's how we feel a good temperature on Earth, like being on the surface of Earth. But if you are in space, actually those temperatures can go super high. So for example, if you go to space with a spacecraft, you can have all the heat coming from the sun hitting directly your spacecraft, and from one side it's going to be super high, and from the other side it's going to be totally dark. So that can even give you some deformation of the structure of your spacecraft, and that can, for example, change the measurement of your orbital control systems. That can affect your electronics. So you have to take into account all these things that are super complex, that can put your satellite into big problems. Okay, so for example, you can have some solar absorption devices. Okay, you can control the system emittance. So what does it mean? It means that your system, for example, of the satellite itself, can be emitting energy, and maybe you don't want that because the heat on your satellite it works well for the electronics of the electronics that are inside the device. So, for example, if you consider microchips. I don't know if there are any electrical engineers or electrical people here, but microchips can work correctly in a super limited range of temperatures. Otherwise, they start doing strange things. They start giving you wrong results. So just take as an example, if you take an iPhone and you expose it to minus 20 degrees, the camera will start misbehaving. You will start seeing some weird figures on the screen. Maybe the screen is not going to function correctly. And this is something that I have seen myself when I was living in a place that was super cold, and at minus 20, the iPhones, only the iPhones were not functioning anymore for them. Okay, so it was many years ago. Maybe they already got better. And this happens it happens exactly the same with the satellites. They stop working if you put the electronics to the wrong, if you expose them to the wrong temperature. So you have two options. Either you protect them to the high temperatures, so the temperature doesn't go too high. Either you take care of the temperature inside by adding, for example, heaters. This thing that we're seeing now in the presentation is a heater. So you apply electrical energy to this heater, to this device, and it starts getting hotter. Okay, so you can put that on top of your circuits, for example, and you can be sure that the system will be on the operating range of the satellite. Okay. So in that way, we can make sure that it works. So seeing the time that I'm actually getting a little bit late, I'm going to go a little bit faster on this part of the Earth. Okay, so this is really nice. This actually was the part that I was working with on Euclid. It's super cool. It's the spacecraft attitude determination, which means how do I determine exactly where I'm pointing to with the satellite, and control of the attitude. So how do I change that attitude when I know where I'm pointing to? So for that, you can have different devices. So you have gyroscopes. So the gyroscopes lets you know what's the speed of my rotation. Okay. So for example, if I'm rotating like this, that device will tell me exactly how fast I'm rotating. That's just to give you an example. You have accelerometers, which is exactly the same, but not with rotation. It's going to be with displacement. So for example, if I'm moving like this, the device, the accelerometer will tell me you're moving to the left. And same thing, if I'm moving like this, okay, you're moving to the right. So that helps you understand where your satellite is and where are you pointing to. And you have a lot of different things. You have sun sensors. Sun sensors are little sensors that tells you, okay, the sun is over there because I have a sensor here that senses exactly where the sun is pointing to. Okay, for example, I can read using electronics. I can read the position of the sun using these sensors. This is really, really nice. You have also magnetorquers. The magnetorquers are devices that help you align to different magnetic fields. Why do I need that in the satellite? So it sounds super, it sounds weird. Why would I need to align to a magnetic field? Well, the Earth has a magnetic field, and I can use that magnetic field and my magnetorquer to align to that magnetic field, and that changes my attitude. Those are many examples of how to use these devices to change and determine the attitude of the satellite. Okay, so I'm going to go a little bit fast with this. Oh, okay, the first thing that you're seeing here is a star tracker. Okay, so these are cameras that look to the sky and tell me where I'm pointing to, because these sensors know where the stars are. So if I'm pointing there and then I'm seeing the Orion's belt, so the camera will know exactly, will recognize that the Orion's belt is there. So I will know exactly what I'm looking to if I'm pointing with my satellite over there. So this is just to give you an example of the many things that you can do with these devices. And the one on the bottom is a sun sensor. Okay. Okay, we're running a little bit of time already. This is a power system. You will need batteries. You will need maybe 2 batteries. Okay, you will need a redundant system, so in a way that if one fails, you have another one. So this is an example. It doesn't look like the batteries of the old phones that we had in the past. There are like special batteries, and they are using systems that make you sure that they will withstand the conditions of in space. Okay, so this is also how the what's the name of this? Oh my God, the word doesn't come to my head. But this is this is a power conditioning unit. Okay, this is a power. So you connect the battery to this device, and this device then puts out the needed voltages and currents that you need for all the subsystems of your satellite. And this is how the connections look like. This is actually what I was seeing every day in Euclid. And this is also how it looks inside to be connecting everything inside the satellite. Okay, so I think we can skip this one from now. I don't know if we have like maybe 5 more minutes, Camilo. So maybe we don't jump so fast on this.
Sure, absolutely. Like we, since we started 10 minutes late, yours, we can continue, and then we can jump later to the final surprise.
Okay, perfect. So, so electromechanical is more or less what I was telling you before. Is one example was the this mechanism that changed the position of an antenna on the Euclid satellite, okay, because the antenna had to be deployed. The antenna was in a certain position when it's launched, and then this changes position and then it's deployed, okay? This is one example. Maybe you will have other electromechanical parts, for example, pyrotechnics, okay? Pyrotechnics, yes, sounds super like a party or New Year thing, but this is actually something needed in space because maybe you need to deploy something and you don't have a motor, you have only potential energy like an elastic or something like that, and you need to break that elastic, and you can put little loads of an explosive load that you can turn on in a specific moment, so you can deploy this part of the satellite in the right moment, okay? And you have a lot of things. There are many different ways to use the electromechanical parts. I'm trying to remember in ExoMars, which is a mission that was going to Mars. It is a joint work between Roscosmos, which is the Russian space agency, and the European Space Agency. And it was super fun when they told me how they did the separation. So because they had this lander, okay? The lander is a device that lands on Mars, and then you have the orbiter, which is actually what gives you the orbit on around Mars. So the lander was attached to the orbiter, and then in the moment of separation, when the lander had to land, actually, you needed to cut the cables of this lander. Okay, so we have a lander here, and you needed to cut the cables. So how do you cut the cables? So what the Russians did in ExoMars program, what they did was actually cutting it with a system of an axe, and it cut all the cables at the moment in which the separation happened. So that sounds kind of brutal, but actually this is how things work in space. Okay, so you needed to cut the cables, so you cut the cables. Then we have the command and data handling. Okay, these are electronics that serves you to process all the data inside the satellite. So you have a lot of data coming to from sensors. You have a lot of data coming from your payload, for example. You have a lot of data coming from Earth. So you need something that puts all this information together and get a sense out of this information, because this information by itself doesn't have any sense. You need to process it. And after that, you can have an useful data that will be useful for your mission. So for that, you need a command and data handling system. Okay. So just to make it simpler, is a computer. This is a tiny computer that it's mounted on the satellite. And then in this computer, you will have the flight software, okay? So the same thing as I was saying before, same as with your computer that has software on top of installed on it, like the operating system or your web browser. The satellite will need special software for processing images, for example, coming from a camera, or the information coming from the sensors need to be processed to have an attitude determination, and then to know exactly how much I need to turn on the propulsion, for example. Okay. So this is something that is not easy and needs to be done by computers in real time, independently from ground, because the satellite at that point can be not in the visual. It sometimes can be out of the field of view. So, if, for example, if I'm in Chile and the satellite is flying over Russia or the North Pole, I'm not going to be able to see it at all. Therefore, I cannot control it. So in that moment, the satellite is on its own and it has to process all the information by its own. And then you have the communications. Okay, the communications is exactly what the words tells you. The satellite is processing all the information by itself internally, but you need to communicate with the satellite. So for that, you will need antennas. Why antennas? Because with the antennas, you can, the antennas help you receive and send that information from or to the satellite. Okay. Yes, for example, in this image, we are seeing some antennas, and I think Camilo is putting some antennas somewhere. If I can read your mind.
Yeah, I'm looking for them.
And
by the way, it's
Sebastian. Whilst
what?
Sorry, hi. It's Wasim. Whilst
Hi.
Camilla's looking for them, you mentioned you're an entrepreneur yourself. How do you see, or how would you like to see education and learning changing towards the fact that we are going to be looking at going to the moon and other places, and why that's going to be important for development on the Earth itself?
Oh, that's a super good question. Actually, yes, and as an entrepreneur, it's super important to me to see that that kids and young people are getting more information about this, because this is the future. This is how this technology is already the future, and the young generations are our future, the future of humanity. So right now, it's going to be me building satellites. It's going to be me maybe helping to send people to the moon, but tomorrow is going to be them. So I think from the private point of view, especially in countries like in Latin America, in which, for example, maybe access to information, everyone has access to information, but maybe in a more curated way. This is something, as a private company, we can create more events, for example, for kids, that can help them get more attracted to these topics, and maybe to involve them also in the development of these technologies from an early age. Okay, so now we have this big antenna. This is like super big. Obviously, this is a zoom antenna. The antennas in satellite are actually tinier. Maybe they are like, it depends on the frequency, obviously. Well, it's not obvious actually, but for example, if you want an antenna that works with frequencies that are more or less maybe 1 gigahertz, maybe this is antenna. This is how you want it. But if you want the antenna to work with higher frequencies, you will need an antenna like the other one that you're seeing right now. It's a signer. Okay, it depends on the frequency. It's the size is not the power. It's not power related. It's frequency related, and all of that needs to be also accompanied with other hardware that help to get the commands, for example, or data from the antenna received then into the satellite. So this is more electronics. This is more units inside the satellite. And then the payload. And we already talked a lot about the payloads and which different payloads you can have. And what we are seeing right now in the image is one special camera with a special filters for a specific application in space. Okay, for some sort of observation. And after you have all these subsystems together, you need to assemble them. You need to test them a lot, and that testing process takes a lot of time. It took years. I worked 3 years with Euclid, but actually people were working on testing for already 5 to 6 years. So that's a lot. That's a lot of time. And yeah, so after you have tested and assembled everything, you launch your satellite, and you start with the operations of it. You start testing it. You start with the insertion in orbit, etc. And this is how more or less how you see people trying to get the best out of the satellite. And this is one example of what you can have with satellite, which is a satellite that looks into the clouds from space and help you understand to make models of the weather in real time. So while you can be under maybe a super strong storm and a tornado, the satellite, it's actually over these clouds, taking pictures and analyzing what is inside of this. Okay, so that has been the presentation of today. I really hope you liked it, and if you have any questions, you can tell to me now. Otherwise, we can, Camilo, you had some
Should we display
idea.
should we display the final surprise? Anybody has any question?
maybe we wait for
We have
one
the
or two
questions there, right? Okay, let's have the questions in our other side. So guys, we have
let's
we
go.
have been on the moon for most of the session. Let's have the Q&A back on Earth.
So you can see everything here in actual size. So you can, for example, see here how the engines are getting prepared for launch, which is really crazy.
So guys, if you have any questions, Sebastian is all yours. He will be more than happy to answer any questions you have while we walk around the Saturn V.
I think there are no questions because the presentation was too clear.
Sebastian, in terms of mining on the moon,
Fantastic.
how realistic do you
Thank
think
you.
that is in terms of mining on the moon, and why would we mine it on the moon as opposed to asteroids?
Would I mine in the moon?
But why would we mine on the moon as opposed to, say, asteroids?
Asteroids. Okay, perfect. Yes, so it all comes down to an economical decision in that case, because if you want to mine for resources, is because you have an economical or a strategic objective. So in that sense, maybe you want those materials because you want to build something, or maybe because it's too expensive to bring those materials to space, and a certain asteroid is closer to the place in which you want to use those resources. So it comes down to an economical decision in that sense.
Makes sense.
Yeah.
Anybody else? Anybody got any questions?
Don't be shy, everyone. Make questions. Maybe we can show them upstairs. Everybody, if you just follow us, we have another surprise here.
Oh, we had a question here, I think, no?
No?
No? Yeah.
Oh, I was just going to make the comment about mining on the moon versus
yes.
asteroids. I guess a big factor there, if I understand correctly, is there's a lot more gravity on the moon. So asteroids are kind of attractive in a way because there's less gravity. So if you can find hydrated asteroids, get the water material with less, delta V or whatever, less
exactly.
Fuel to retrieve it. Yeah, but
You need less fuel per liter, let's say.
Yeah, exactly.
Yeah.
Exactly.
Cool. Should we go upstairs?
Yeah, let's do it.
Okay, let's go upstairs then. Is everyone following us? Okay.
So everybody just stand up in front of here, and when you read up, yes, just go inside.
You can come here to follow us.
You can come. It's safe.
Yeah, if you come closer here to this door, at some point the word "up" appears, and you click it with the joystick by pointing at it.
So what do you think, Wasim?
Absolutely amazing. This is absolutely phenomenal.
But look at down, towards your feet.
Here.
Cool.
Do you see that bird? Okay, perfect.
We're here. Come.
Yeah.
I'm scared of heights.
Yeah, it's a little bit, but just remember, this is all digital. You are completely safe at home. Yeah, wonderful.
Real.
Do we have any more questions for Sebastian before we close our session?
There's always going to be tons
I
of
really
questions.
hope you liked it, guys. And yeah, it was a pleasure to give you this lecture.
Thank you so much, Sebastian. It was such a pleasure for you to be here. So I hope everybody enjoyed it. Rushing in here and outside. This is the kind of stuff that you can expect when we kick this off. So thank you for joining.
Yeah.
Thank
you,
you.
Rigor, for joining. The session will remain open. Feel free to join us within 45 minutes, where we will be talking about astrobiology and the origin of life. It will be under the same code, so you can stay. In the meantime, just go grab a coffee, chillax in the meantime, and we will see in this same session within 45 minutes. Thank you, sir.
Okay.
Yeah,
Thank you, man.
There you go. Yeah, pleasure.
Yeah.
Mhm.